in the last class we have discussed about determinant of a two-dimensional matrix representing the area, and in fact, three-dimensional matrix, if the determinant is taken, it will be actually representing a particular volume, and that volume will be the of the parallelepiped, which will be formed using the basis vectors. Okay, for example, suppose I have a vector in this particular direction, another vector in this particular direction. Okay, now these two vectors can actually form a parallelogram, and if the third vector is not in this particular plane, suppose the third vector is in this particular direction, okay, which is not in this particular plane, then naturally you can form a 3D figure. You can form a 3D figure like you can form a 3D figure like this, right? One second. And that 3D figure will be having a particular volume, which will be obtained as the determinant. Okay. So that is about the determinant of a 3x3 matrix. Okay. Right. Now we will consider different cases. Suppose the determinant equal to 0. What does that mean? We call certain matrices as non-invertible matrices or singular matrices. We call certain matrices as singular matrices or non-invertible matrices. Okay, what is meant by a singular or non-invertible matrix? If for any matrix, if the determinant of that matrix is turning out to be 0, then we call it as a singular matrix. Okay, if the determinant of any matrix is turning out to be 0, then we call it as a singular matrix. I'll give an example for a singular matrix. Let us consider the case of, let us say, we have 2, 4, 1, 2. We know this column is C1, this column is C2. We have the idea of now the 2D picture. Now 2, 4 will be 2, 4. It will be this vector, right? 2, 4. And naturally 1, 2 will be along the same line. So these two vectors are lying on the same line. Naturally the area will be 0. So that is it cannot span the 2D space. That is what it means. Now, if you consider a three-dimensional vector, let us say a three-dimensional space, vector space. For example, I have a 3x3 matrix. Let us say B is a 3x3 matrix. B is a 3x3 matrix 1, 0, 1, 1, 1, 0, and 0, 0, 1. It's a simple matrix. Now, if you consider the determinant of this matrix, it will not be 0 because 1 into, you know how to evaluate the determinant, right? 1 into this particular minus determinant, which is 1. So that is 1 minus 1 into this is 0. And last one is 0. So rest is also 0. So the answer is 1, which means it is not equal to 0. So it is a non-singular matrix, which implies it will have the ability to span the 3D space. This particular matrix will span the 3D space. Now, if I consider a C matrix, another matrix, which is, let us say, 1, 2, 1, 3, 1, 2, and let us say 4, 3, 3. Okay. Now, what will be the determinant of this particular matrix C? What will be the determinant of this particular matrix C? If I take this particular matrix, 1 into 3 minus 6, which is minus 3. See, 1 into 3, 3 minus 6, which is minus 3. Minus 3 into 6 minus 3. So minus 3 into 3 plus 4 into 4 minus 1. So 4 into 3, which is equal to, this is minus 3 minus 9 minus 12 plus 12. So that is naturally 0. Now what does that mean? It means this particular matrix have three columns. So the three columns are C1, C2, and C3. Now these three columns cannot span the 3D space, or actually it will lie on a single plane. It will lie on a single plane. So naturally the volume formed, if you have three vectors, suppose you have one vector here, one vector here, another vector in the same plane. Can they form a parallelepiped? It's not possible, right? The volume formed by these three vectors as edges of a parallelepiped will be naturally, volume will be 0. That's what we are obtaining as 0 in the determinant. Okay, is that clear? So we will just give you a simple problem to work out. It is given that the question is, it is given that matrix A is, it is given that the matrix A is a singular matrix. You need to find out the value of x. So the question is, find the value of x, find the value of x if the matrix A is singular. That is the question. So it's a simple question. You can just try to find out the answer. 2, 3, 4, 7, 1, minus 2, and 5, minus 2x. This is the question. 2, 3, 4, 7, 1, minus 2, 5, minus 2x. This is the question. So you can check what is the value of x which will make this matrix singular. This is the particular matrix. What should be the value of x which will make the matrix singular? You can all try, and if you get the answer, you can just message in the chat. I'll give 2 minutes. You can try now. Any answers? Any answers? Yes. Is it coming out as 5? I think you made some mistake. This matrix is singular means the determinant must be 0. Yeah, Anumol, you are right. Answer is minus 6. You will get it as minus 6. So maybe, okay, correct answer. So you can try that. I'm not working it out completely. Only thing is you find the determinant, equate it to 0. You can get the value of x as minus 6. That's it. Simple. Okay. So yeah, answer is minus 6. I think Anumol, Ashwati, Ashehin, Srilakshmi, Sudhakar, Arvind, all of you got a correct answer. Sujit, your minus sign is not there. Minus 6 is the answer. It's not 6. Okay. Right. Right. We are moving on to the next topic. Now we'll see what is meant by n, or how do you take the inverse of a matrix. Okay, that is our next topic. How do you take the inverse of a matrix? Inverse of a matrix, and what is the inverse of a matrix, and what is the implication of inverse of a matrix? Okay. So you know what basically a matrix does. A matrix is actually an operator which can represent a system. A matrix basically represents a system. It represents a system. Okay. Or it can represent any system, normally linear systems. Okay, so let us consider what is meant by the inverse of a matrix. A inverse is defined to be, it is given as 1 times 1 by determinant of A into adjoint of A. This is the definition for inverse of a matrix. Now, what is adjoint of A? How do you evaluate adjoint of A? How do you evaluate adjoint of A? Let us see adjoint of A. Adjoint of A. Adjoint of A is, it is the transpose of cofactor matrix. We take transpose of, please screen, someone has started sharing their screen. Please don't share your screen accidentally, so that you will miss my screen. That is the problem. Okay. Now I hope my screen is visible. Okay. Right. So transpose of cofactor matrix. Cofactor matrix, we take the cofactor matrix and then find the transpose of that. Okay. So what is meant by adjoint of a matrix. So we'll take an example of how to evaluate the transpose of a matrix. How to evaluate how to get the cofactor of a matrix. Suppose I have a matrix. Let us say A is given by, I have A, B, C, D, E, F, G, H, I. My cofactor matrix is given by, let us say A cofactor is given by, I'll take the first point, that is the first row, first column. So if I consider this part, this element, you need to remove this row and this column and find the minor of this particular smaller matrix. So that is EI minus HF, correct? EI minus HF. Now, how to get it, its sign? It's simple. Minus 1 to the power I plus j, minus 1 to the power I plus j times the determinant of the minor matrix, which is obtained by removing the row and column which is numbered I and j. So it's very simple. If I take first row, first column, I and j are 1, 1, correct? I and j are 1, 1, which means minus 1 to the power 2. So minus 1 sign will be turning into plus 1. A minor means you remove first row and first column and you obtain the smaller matrix EFGH, EFHI, right? So you did find the determinant of this EI minus HF. So plus sign comes because minus 1 square into EI minus GH. This will be the first term. Similarly, if I want to find the second term, that is I is equal to 1 and j is equal to 2. So first row, second column. Okay, first row, second column, which means first row, second column means minus 1 to the power 1 plus 2, which is minus 1 cube, which is equal to minus 1 into first row gone, second column gone. So what is left out is D, G, F, and I. Now you take the minor of that. So, or a determinant of that, Di minus GF. That we should post here with a negative sign, right? This is how you evaluate the cofactor of a matrix. Now take the transpose of that cofactor to get the adjoint of the matrix. Okay, so for a 3 by 3 matrix, you can take an example for a 3 by 3 matrix and do it from home. I'll consider an example with 2 by 2 matrix because that is very easy to find. We'll not spend some more time on how to evaluate cofactor and adjoint and all, because that is already learned in your +2 maths. I'll write down the case of a 2 by 2 matrix first. So first is A, B, C, D. This is a 2 by 2 matrix. How do I get the inverse of this particular matrix? First, I need to take 1 by determinant of A into adjoint of A, right? Now, what is determinant of A? It will be nothing but AD minus BC, correct? It is nothing but AD minus BC. Now, I need to take the transpose of cofactor matrix. So, first cofactor matrix. What will be the cofactor matrix? Cofactor of A. Cofactor of A will be, I'll take first row, first column. So, if I take the first element, this is gone, this is gone. What is left out is D. And I need to write the sign positive because 1 plus 1 minus 1 to the power 1 plus 1 is positive, right? 1 plus 1 is 2. Minus 1 square is positive. Now, I take the second element. If I take second element B, first row and first column, first row and second column will be gone. So, what is left out? C. And the sign of C will be minus because minus 1 to the power 1 plus 2, correct? Similarly, if I take the cofactor corresponding to C, CD and CA column and CD row will be gone. Minus B will be coming because again row is 2, column is 1, right? So 2 plus 1 is 3. Minus 1 plus 3 is negative. Similarly, last if I take D, then CD and BD will be gone. A will be there. Here it will be minus 1 to the power 2 plus 2. So that will be positive. So I'll get A, right? So this is cofactor of A. Now I should get the adjoint of A. What is adjoint of A? Adjoint of C. See, this is 1 by determinant A, 1 by determinant A into adjoint of A is the transpose of this particular matrix, right? So D minus B minus C and A. So this is the inverse of a two-dimensional matrix. Okay. Now I'll give you an easier way to write the inverse. Once you have the matrix, okay, it is very easy to write the inverse of this particular matrix. You always need not go for cofactor, transpose and all. You can write it simply as 1 divided by determinant, what is AD minus BC. Then you write the matrix, interchange the diagonal elements, which means DA. Put opposite signs for the other diagonal, opposite diagonal. So here it is plus B, here it plus C. So I'll put minus B minus C. So interchange the diagonal elements. For the opposite diagonal elements, you put negative sign. Divide the whole matrix by determinant. This is the simple rule to evaluate the inverse of a 2 by 2 matrix. Okay, this is a simple rule to evaluate the inverse of a 2 by 2 matrix. We will consider an example here. Let us consider an example of a 2 by 2 matrix. So I'm taking a matrix A is equal to 1 minus 1, 1 plus 1. Okay, this is a particular matrix. We'll see what happens in the process of taking an inverse. So if you consider this as a system, we'll plot the column space of that particular matrix. We'll plot the column space of that particular matrix. Let us see how it will be. 1, 1 is the first vector. The first column is 1, 1. Correct? The one, yeah. I'll repeat. 1, 1 is the first column. Sudhakar, you want me to repeat the process of taking inverse of a matrix or 2 by 2 matrix? You want me to repeat the inverse of a matrix, correct? I'll tell you how to take the inverse of a matrix. Last step in inverse for the 2 by 2 matrix, right? Okay. Last step in the inverse is, see, if I want to get the inverse directly for a 2 by 2 matrix, the first step is take the determinant. 1 into 1 minus 1 into minus 1. So 1 plus 1, that will be 2, correct? Into, now you just interchange the diagonal elements. Here the diagonal elements are both 1. So I'll have 1, 1 itself. Now you just change the sign of the opposite diagonal elements. Here the sign of 1 is minus, so I'll change it to plus 1. Here the sign of 1 is plus, so I'll change it to minus 1. That's it. It's very simple. You just keep the diagonal. So you just interchange the diagonal elements. You just change the sign of the opposite diagonal elements. That's it. Okay. So this is going to be the inverse of this particular matrix, and we'll see what it. Yeah. Okay. We'll see what it means in geometry. Okay. See, 1, 1 is a vector in this particular direction, correct? 1, 1 is a vector in this particular direction. So that is 1, 1, right? And minus 1, 1 will be minus 1 in x direction, plus 1 in y direction. So that will be a vector in this particular direction, correct? So minus 1 plus 1. So this is a vector minus 1, 1. So this is the matrix A, or this is the column space of the matrix A, correct? And we know what is the magnitude of this vector. The magnitude of this vector is, if I take the magnitude of the vector, that is nothing but you apply Pythagoras theorem, root of x component square plus y component square. So root of 1 plus 1, nothing but it will be root 2. So root 2 will be the magnitude of this vector. Similarly, root 2 will be the magnitude of this vector as well, correct? So that is a particular column space, a matrix and its column space. Now what happens with the inverse? Let us see what is the inverse. The inverse is 1 by 2. I have taken the determinant. Determinant is 2 into 1 plus 1 minus 1, 1, which means I can take it inside. All the factor should be taken inside. So all elements will be divided by 2. So this will be 1 by 2. Since I am taking this 1 by 2 inside, this will be 1 by 2. This will be minus 1 by 2. And this will again be 1 by 2. Okay. So this is the inverse matrix. Now what it means, this is the inverse matrix. What it means is, I'll plot the column space of the inverse matrix also. I'll plot the column space of the inverse matrix also. What it means is, see, 1 by 2 minus 1 by 2, which means I have x component as 1 by 2 and y component as minus 1 by 2. So that point will come here. That point will come here. This is the point. 1 by 2 minus 1 by 2 is this column, right? Another is 1 by 2, 1 by 2. So that will be this column. 1 by 2, 1 by 2. Okay. And what is the magnitude of this particular vector? You have x component as 1 by 2, y component as 1 by 2. So the magnitude will be root of x component square plus y component square, correct? Which is equal to root of 1 by 4 plus 1 by 4, which is nothing but root of 1 by 2. So that is 1 by root 2. That is the magnitude of this particular vector. The magnitude is 1 by root 2. This magnitude is 1 by root 2, right? This vector magnitude is 1 by root 2. Again, this vector magnitude will also be 1 by root 2 because again, the terms are same. So this will be 1 by root 2. Okay. So you can think of the inverse of a matrix as a system doing an operation. If you consider this particular matrix as a system and it is doing some operation, what the inverse matrix does is it will just revert back that operation. Okay. Or if I consider a system to be A, okay, if I am giving an input to be X, you are getting an output to be Y. Now, what does the inverse system does? The inverse system will actually give you back the input. The inverse system will actually give you back the input. If you give an input X and if you get the output Y, and if I apply the inverse matrix or inverse operation, you get back the original input X. Now, is this always possible? No. Sometimes it will not be possible. For example, I'll give an example of a system which will not have an, see, until this point, is it clear to all of you? See, I have taken the inverse space is also clear to you. I'll tell you an example for a particular case where you cannot take the inverse of the system. You cannot take the inverse of the system, right? It's very simple. You can think when the inverse is not possible, because we are dividing by the determinant in the inverse process, right? We are dividing by determinant in the inverse process. See, if the determinant is 0, you will get something like 1 by 0, which means it is non-invertible, right? So if A is a singular matrix, if A is a singular matrix, it implies it is non-invertible. It is non-invertible. If A is a singular matrix, it is non-invertible. That is a very important point. You should note it down. A singular matrix is non-invertible. I'll give an example of a singular matrix. See, suppose I have, you can understand what I meant by this system. Okay. I'll just give an example for that particular system. Suppose I give a input X. So the output of that system is, for example, output of that system is X square. Now, you cannot get back X from that system because the inverse is not possible, or it's a non-invertible system. Why is it so? Because if I give 2 as the input, I'll get 4 as the output. If I give minus 2 also as the input, I'll get 4 as the output. Which means, observing the output, you cannot say what was the input. Or, for a unique input, the output should be unique. Or, the output should always be mapped to a unique input. Then only it is possible to get back the input from this. Because if I give minus 2 as input or plus 2 as input, I am getting output as 4. So, observing the output, I cannot predict what is going to be the what was the input. Correct? Which means I cannot say what was the input. So it is not an invertible system. Okay. If determinant is 0, that means it is a singular matrix and it is a non-invertible matrix. Okay. It is a non-invertible matrix. If determinant is 0, it means it is a singular matrix as well as it is a non-invertible matrix. Is it clear? Do you have any doubts? If it's clear, I can proceed. If it's clear, I can proceed. Okay, Akshay Mahan, yes, no doubts. Okay, right, it's clear. Right, so I'll introduce another matrix which is special. So we have seen singular matrix. Now I'll introduce another matrix called as orthogonal matrix. Orthogonal matrix. Okay. Orthogonal matrix. This is a very important class of matrix because you'll be using a lot of orthogonal matrices in your engineering subjects. Okay, so I'll take one particular example and see what are the properties and see and observe the definition later. I'll consider a particular matrix to be 1 by root 2 minus 1 by root 2, 1 by root 2, and plus 1 by root 2. Okay, so from the word orthogonal, you must have heard about the word orthogonal before. Orthogonal means 90 degree, right? This is what you have in mind. Or basically, orthogonal means 90 degree is correct to some extent if you consider a 3D space or 2D space, but dimensions may increase. So generally, what does orthogonal means? Generally, orthogonal means dot product will be 0. Generally, orthogonal means dot product equal to 0. This is the basic idea of orthogonality. Dot product equal to 0. Now, how do you take the orthogonal? How do you take the dot product of these two columns? Suppose I have column 1 here, column 2 here. Column 1 is 1 by root 2 times I vector plus 1 by root 2 times j vector. Correct? Column 2 is 1 by root minus 1 by root 2 times I vector plus 1 by root 2 times j vector. Correct? 1 by root 2 times I vector, 1 by root 2 times j vector here. And this is minus 1 by root 2 I minus plus 1 by root 2 j. How do you evaluate C1 dot C2 if you want to find the dot product of these two columns? It's very simple. How do you evaluate the dot product of two vectors? You just multiply the I components, you just multiply the j components and add it up. Correct? So I have 1 by root 2 into minus 1 by root 2, which is minus 1 by 2. Correct? 1 by root 2 into minus 1 by root 2 is minus 1 by 2. Plus, I'll add up the other components product 1 by root 2 into 1 by root 2, which is 1 by 2, right? So I have the answer to be 0 here. So I can say these two columns are now orthogonal, right? These two columns are now orthogonal. Now this is the fundamental idea behind orthogonality. Now, if it has to be an orthogonal matrix, then it has to obey some more properties. Just columns are orthogonal is not enough. I need to get the inverse of that particular matrix equal to the transpose of the matrix. Okay, I need to get the inverse of that particular matrix equal to the transpose of the matrix. I'll see what is the inverse of this particular matrix. Let us see what is the inverse of this particular matrix first. Okay, let us consider what is the inverse of this particular matrix. Right. How do you get the inverse of this particular matrix? See, you have A here. So A inverse is pretty simple because that is a 2 by 2 matrix. So 1 by determinant of A, 1 by root 2 into 1 by root 2, that is 1 by 2, minus 1 by root 2 into minus 1 by root 2. So again minus 1 by 2. So 1 by 2 minus 1 by 2. So that is 1. 1 by 2, 1 by 2 minus 1 by 2. That is 1. Okay. So determinant is 1. And how do you put the adjoint matrix? Interchange the diagonal elements. Here the diagonal elements are same. I can write the as 1 by root 2, 1 by root 2 itself. Now you put opposite sign for the other diagonal elements. So this is minus 1 by root 2. So I need to write 1 by root 2 here because I have changed the sign. This is 1 by root 2. So I need to put minus 1 by root 2. Correct? So this is what is C, 1 by 1. So there is 1. So A inverse is nothing but 1 by root 2, 1 by root 2, minus 1 by root 2, and 1 by root 2. Now you can see this is nothing but the transpose of this particular matrix. Okay. A inverse is taken and we obtained the transpose of that particular matrix. Correct? A inverse is taken and you obtain the transpose of this particular matrix. This is the basic definition of an orthogonal matrix. This is the basic definition of an orthogonal matrix. An orthogonal matrix will have A inverse equal to A transpose. One more thing we can prove from this particular thing, because we have learned about determinants. What we have learned about determinants is determinant of A transpose will be equal to determinant of A inverse. So I will take determinant on both sides. So I can write determinant of A inverse equal to determinant of A transpose, right? Determinant of A inverse equal to determinant of A transpose, right? What is determinant of A inverse? That is nothing but 1 by determinant of A. We have learned it in last class. And what is determinant of A transpose? That is nothing but determinant of A itself. That is also what we have learned in last class. So if I take determinant of A to the right side, it will become determinant of A, the whole square, correct? Determinant of A into determinant of A. Determinant of A whole square becomes left side is what? What does it mean? It means determinant of A is going to be either +1 or -1. Determinant of A is going to be either +1 or -1. And this is, remember, this is a property peculiar to only orthogonal matrices. Once you have A inverse equal to A transpose, you can say determinant of that matrix is going to be either +1 or -1. Is it clear? You want time to take down it as notes? Just you need to write these 2 points. A inverse is A transpose. You write an example matrix, this, and you write dot product is 0, and then determinant is +or -1. So 3 points you need to remember about orthogonal matrices. First point is it will obey A inverse equal to A transpose. Second point is its determinant is going to be either + or -1. Third point is all the columns, if you take different columns and dot product, the dot product is going to be 0. Dot product is going to be 0. So you can remember these 3 points, right? You should not forget these 3 points. These 3 are the key points regarding orthogonal matrices, right? Shall I move? Yes, if determinant is + or -1, does it guarantee that the matrix is orthogonal? No, 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 no. Manchunad, your doubt, it is. See, if the matrix is orthogonal, then determinant equal to + or -1. If the matrix is, if the determinant is + or -1, that does not imply the matrix is orthogonal. No, that is not true. The converse is not true. If the matrix is orthogonal, determinant will be + or -1. Determinant, see, I have another matrix. See, you can see a n number of matrices whose determinant is 1 or -1, but they are not orthogonal. I'll take an example. Okay, you can just check. If I have, see, if I have a matrix like, suppose 3, 4, what is that? 10. Okay, sorry, 10 is not correct. Okay, 11, 1. Okay, what is the determinant? Determinant is 12 minus 11 equal to 1. But does that imply it is orthogonal? No, it's not orthogonal, because they don't even C1 dot C2 is not equal to 0. First point is breaken. Second point, A inverse is not equal to A transpose. That is also broken. So +1 or -1 determinant does not guarantee it as an orthogonal matrix. If it's an orthogonal matrix, then determinant is going to be + or -1. That's it. Is it clear? Okay, now shall I give you right? I'll give you one. Okay, someone is joining. Okay. Right. We'll be continuing with one problem I'll give you. Okay. So we have learned what is an adjoint matrix now. I'll give a question for you to think. Okay. I'll give one question. Question is, given, you can take it down, given determinant of a 3 by 3 matrix is, given determinant of a 3 by 3 matrix A S 6. Now, then find the determinant of adjoint of A. Adjoint of A. Okay, so we know adjoint of A is a new matrix. You are given the determinant of A to be 6. You need to find the determinant of adjoint of A. This is the question. What is the answer? You can try. I'll give you 2 minutes. Yes. All of you can try. I'll give 2 minutes for all. Already the answer is there in the screen, so you should not look into the chat. Yeah, correct answer is coming up. Darshana and Manjunath, both of you got a correct answer. I'm not reading out the answer because someone, if they're trying, let them give some more time. Meanwhile, you can ask any doubts. If you have any doubts, you can unmute and ask, or you can type in chat. Both are okay. Okay. So okay, answer is no more answers. We don't have much time to waste because only we are getting 1.5 hour sessions. Okay, so I'll start again. Okay, I'll start doing it. Answer is 36. 36 is the correct answer. We will have a formula for this one. Okay, what is the determinant of adjoint? That is the question. I know the inverse of a matrix is given by 1 by determinant of A times adjoint of A, correct? But this determinant of A is a number. It's a number, correct? So I can write that as 1 by, let us consider that number to be alpha, 1 by alpha into adjoint of A, right? Now, if I take this alpha to the left side, I'll get adjoint of A is nothing but adjoint of A is equal to alpha times A times A inverse, right? Alpha times A inverse. Now we know A inverse is a 3 by 3 matrix. Now if I take determinant on both sides, determinant of adjoint of A will be equal to determinant of alpha times A inverse, correct? Now we know, we have learned the property, if a number is multiplied by a matrix, the result is going to be alpha raised to n, correct? Where n is the order of the matrix. Order of this matrix is nothing but 3 by 3, correct? So alpha raised to 3 into determinant of A inverse. And you know what is the determinant of A inverse? That is 1 by determinant also. So here alpha cube into 1 by determinant of A. And our alpha is, what is alpha? Alpha is determinant of A. So that is alpha cube into 1 by alpha, that is equal to alpha square. Alpha is determinant. So answer is 36. Okay, answer is 36. I'll repeat. A inverse is 1 by determinant A into adjoint A. And determinant of A is a number. So I'll write that number as alpha. If I take alpha to the left side, that becomes adjoint of A equal to alpha times A inverse. Now if I'm taking a determinant on both sides, it becomes determinant of adjoint of A on left side and determinant of alpha times A inverse inside. Now, we know determinant of K times A is equal to K raised to N into determinant of A. That is a property which we have learned, right? That was a property which we have learned. So this property, if you recollect, I can apply that property inside this one. So alpha is taking out as alpha cube because here the order is 3. Alpha cube into determinant of A inverse is nothing but 1 by determinant of A. So that is again alpha itself. So alpha cube by alpha, answer is alpha square. Is it okay? So I'll write it as a formula. Determinant of adjoint of a matrix is equal to determinant of that matrix to the power n minus 1, where n is the order of the matrix, In this particular problem, we have determinant of A is equal to 6 and it is a 3 by 3 matrix. So adjoint of A becomes 6 to the power 3 minus 1. So 6 to the power 2. So 36 is the answer. Hope all of you are clear with that concept. right? Hope all of you are clear with this concept. Shall I proceed? Okay. Do you want me to repeat? Nobody is responding. Okay, clear. Okay, so that's clear. So I'll proceed. Okay, right. I'll proceed. Okay. All right. So I'm moving forward. I'll just see. Someone has asked me a doubt. Okay, I think Vishnu has joined. Vishnu told me that Vishnu will be joining late today. I think Vishnu has joined. Hopefully, but the question I'll plot here. I mean, I'll post the question here. He wants to. This was a gate question. He wants to find the determinant of a 4x4 matrix, which is 2 1 1 1 2 1 1 1 1 2 1 and 1 1 1 2. This was the question. This was a gate question which was asked mechanically. Now you can solve it, but it is easy to solve. You can solve it using the old method, which is very time consuming, but it is easy to solve once we have the knowledge about eigenvalues and its properties. Eigenvalues and its properties. Okay, so you can all try to solve this by some other method. But once we learn eigenvalue and its properties, I'll solve this very easily. It will take only 1 minute to solve this particular problem using eigenvalues and its properties. So Vishnu, I'll be discussing this particular problem once we discuss eigenvalues and its properties. Okay, you can keep it in mind. If I forgot this, you can remind me. Okay. So the answer for this is going to be 5. You can check with some other methods. The answer is going to be 5. And it is very easy once we know eigenvalues and its properties. Okay. So for the time being, I am moving on with another property of a determinant. So, see, a lot of other properties are there. We'll be discussing few of them. For the time being, let us consider one more particular property. I'll just, is there any method with row operations? Yes, you can do row operations. See, you can convert it into echelon form and also find out the determinant. Taking pivot elements. That we will learn once we are starting with rank of matrix. I'm planning to cover rank of matrix also today. So probably that method is also good. But I believe this eigenvalue method is the easiest method. Okay, that method is okay. Echelon form method is okay, but the best method to solve that particular problem is eigenvalue idea. Okay, so we'll definitely solve it using echelon form also. Right. So I'll introduce another concept, which is maybe you can understand it once we draw the picture first. Suppose I have a rectangle here. Okay, the rectangle is having a length of 3 and a width of 2. So we know what is the area of this rectangle, right? The area of this rectangle is nothing but 6, correct? No, I plot the diagonal of this. Okay, now if I take this much units, this is 0 0 point. If I take this as 0 0 point, this will be 3 0 point, right? And this point will be 3 2 point, right? And this point will be 0 2 point. It's if this is in the mesh, if that is in the mesh of, let us say, HY coordinate system, that is going to be the points, right? This point will be 3 0, this point will be 3 2, this point will be 0 2, this point will be 0 0. If I take another vector from here upwards, okay, or another point here, I'll take reflection of this particular vector and I take 2 more units to upward. So it will reach the point, I think, if I take 2, so it will be 3, 4, because X component is not changed, Y component is increased by 2 units. And I plot this line. Okay, so this becomes a parallelogram, right? This becomes a parallelogram. This becomes a parallelogram. I'm first considering this parallelogram. Okay, I'm first considering this parallelogram. Now I can also consider another parallelogram here. Okay, I'll use different color. This is another parallelogram, or this is a rectangle basically, right? Now, will the area of this parallelogram, this particular parallelogram, and that of the rectangle same? That is my question. Will that areas be same? The top parallelogram and this rectangle, will the area be same? It will be same because you can think of it as I am dividing this top parallelogram into two parts. This triangle, and this triangle will have same area 1 and 2. Correct? Because this is a parallelogram and I have drawn the diagonal. Diagonal will split it into two different areas. Now, if I consider 2 and 3 is another area, 2 and 3 will also be same. So naturally, area 1 plus 2 will be equal to area 2 plus 3, which means my parallelogram, which is drawn like this, will have the area similar to that of the rectangle drawn like this. Correct? The parallelogram which is drawn like this will have the area similar to rectangle which is drawn like this. Correct? Now, if I draw the column space corresponding to this particular rectangle, what will be the column space? The column space will be this vector and this vector, right? That is, this vector is 3, 0 and the other vector is 0, 2. This will be the column space of this particular rectangle. Now, what will be the column space of the parallelogram? They are considered, they are defined by two vectors. One is this particular vector, right? That is 3, 2, and the other one is 0, 2. So I have 3, 2 and 0, 2. Now you can see 3 plus 0 is 3, 0 plus 2 is 2, and the other column is remaining the same. Correct? See that this particular column is remaining the same. These two columns added up to get the new column. Now, what is the determinant of this part? 3 into 2, that is 6 here. Determinant of this is out of 6. Now, that gives you an interesting result. What it means is, if you have a, you need not worry about the area part. Area part I have drawn to be for you to better understand. The idea is, if I have 6, 3, 7, 1, this is a 7, 4. This is a particular matrix. What is the determinant of this matrix? This matrix's determinant is 6 into 4, 24 minus 3 into 7, 21. Right? Now, if I add up these two columns, this is C1 and this is C2. If I add up these two columns and write it as first column, 7 plus 6 is 13. 3 plus 4 is 7. Again, the second column is left as such. I do not make any changes to the second column. What is going to be the determinant? 13 into 4. That is, 13 into 4 is, see, I have made a, 6 plus 7 is 13. 3 plus 4 is 7. 13 into 4 is 52. 52 minus 49 is 3. What is the answer here? 24 minus 21 is 3 here also. Correct? 6 into 4, 24. 24 minus 21 is 3. 13 into 5, 13 into 4, 52. 52 minus 49 is 3. Which means if you add up all columns and put it as the first column without making any changes to the other columns, determinant will remain the same. That is the idea which I used to try to convey using this rectangle and parallelogram. If it is not clear to you, you can think about this particular, I'll draw again. You can think about this particular matrix 3, 0, 0, 2. The determinant is 6. You draw the column space of this. That is 3, 0, 0, 2. Right? We have learned that its area, this rectangle's area will be the determinant. Now I add up these two columns. So that is 3, 2. 3 plus 0, 0 plus 2. Right? And the other column is left as such, 0, 2. Now you plot this column space. This column space is 3, 2 is the first vector, right? Second vector is 0, 2. Now these two vectors form another parallelogram, and this parallelogram area will be similar to this rectangular area. That is the idea which I try to prove. Is the concept clear to you? It's clear. Okay. Okay. Should I repeat? Okay. You might have some doubts. You can chat, write it in chat window. I'm breaking for my 5 minutes. I'll be back by 5:25. Okay. So please write down your doubts. When I'm back, I'll discuss it. Okay. Okay, I'm back. Do you have any doubts? If everything is clear to you, we'll move on to the next. Property. We'll clearly. Okay, it's everything is clear to you. Okay, so we'll move on to the next topic. So, sir, a lot of properties are there for determinant, which you might be knowing, many of you. See, first, I think I have not discussed this property. That is, if you interchange any rows, any two rows or columns, the determinant becomes negative. That is, if I consider 3, 0 and 0, 2, the determinant is 6, right? If I interchange the rows and columns, that is 0, so any two rows, 0, 2 and 3, 0, the determinant becomes -6. Now, what does that mean? It means, see, 3, 2 is this particular matrix, and that area is this particular area, right? If I put 0 to first, that is, if I put this column first and this column second, then it is actually giving me the area of the other side of this rectangle. Okay, you can think of this rectangle as having two areas, and area is one particular physical parameter which is assigned a direction. Area is having a direction. Area is having direction. Okay, so the direction of this particular area is outside the board, or it is a normal outside the board, normal towards the outside the board. And you have another area for this particular rectangle which is in the opposite side of this rectangle, which is into the board. The direction of that area will be into the board. Okay, am I audible? My mic is audible, right? Okay, so that particular area will be obtained when you interchange the row and column, because it will be actually, it is taking something similar to cross product. So you know, A cross B is not equal to B cross A. It is actually minus of B cross A. So in both cases, we are getting area of different faces. That is why the sign is plus here and minus here. Plus sign means it is giving you the area of this rectangular which is facing us. Okay, minus sign means it is giving you the area of the rectangle which is the opposite side of this particular board. That is the meaning of negative sign in area. That is what is happening if you interchange two rows of columns. Similarly, another point is, so I'll write that point here. If any two rows or columns are interchanged, then determinant becomes negative of same value, negative delta. If initial determinant was delta, if you interchange two rows or if you interchange two columns, determinant becomes minus delta. Okay, right. One more point we'll discuss about determinant. We'll move on to the rank of the matrix. The other point is, if you have any two rows same, or if any row is a linear combination of other two rows. I'll consider a particular example to explain this concept. I'll consider a particular 4x4 matrix. Okay, see, I'll have or 3x3 will be easier, because to calculate the determinant, 3x3 will be easier. So consider this particular determinant 2, 3, 1. This is one row of the matrix, 1, 2, 1, and this row is 3, 5, 2. So I have row 1 here, I have row 2 here, and I have row 3 here. And I have intentionally written it as row 3 is a linear combination of, linear combination means weighted sum, right? Or alpha times R1 plus beta times R2. I have intentionally written it as alpha times R1 plus alpha beta times R2. Here alpha equal to beta equal to 1, which means if I take R1 plus R2, 2 plus 1 is 3, 3 plus 2 is 5, 1 plus 1 is 2. In this case, R3 is equal to R1 plus R2. Then determinant will be equal to 0. This is the last point regarding the properties of determinant. That is, if you take the linear combination of any two rows and that indicates the third row, then the determinant will be 0. Now that gives you an insight about one more thing. That is, if the determinant is 0, then that implies all these three rows, all these three columns are lying in the same plane. That happens when one of the column can be written as the linear combination of other two columns, or one of the rows, both are same, A and A transpose. See, if I say A, that is applicable to A transpose also, because determinant of A and determinant of A transpose are same, correct? So under that case, if you have any column which can be written as a combination of other two, then naturally the determinant is going to be 0. Then naturally the determinant is going to be 0. See, this is what I have done in the problem where we have taken a particular problem. See, I think I have discussed a particular problem. Yes, in this particular problem, right, I can easily write the answer is -6, because this question was to find the value of x if the matrix is singular. The matrix is singular means the determinant is 0. Under that case, you can always write third row or any row. Any row is a combination of other two rows. See, if I am checking the third row, I can see 5 is nothing but 7 minus 2. Minus 2 is nothing but 1 minus 3. Then this value must be this element minus this element. That is -2 minus 4, which is equal to -6. You need not always write the expression to evaluate the complete determinant. You can easily check for this linear dependency first. Sometimes it may not be possible. So for example, I'll write one particular case, say 3, 4, 5, 2, 9, 1. Okay, and if I have, right, I have, let us say 7 here, alpha here, and 7 here. Okay, can you quickly say what is alpha? Can you quickly say what is alpha for this determinant to be 0? Alpha is going to be, what is alpha? It's 22. Yes, you can check, because I have taken 2 times row 2 plus row 3, sorry, row 1 equal to row 3. So 4 plus 3, 7, 2 plus 5, 7. So naturally this must be 9 into 2, 18 plus 4. This must be equal to 22. Then this determinant will be equal to 0. Okay, so yes, then this determinant will be equal to 0. Correct, Arvind, you got the correct answer. 22 is the correct answer, because we can easily think of this singular matrices as one row or one column is linearly dependent on other columns or rows. This is the basic idea of determinant equal to 0. I hope the ideas are clear. So we will move on to our next topic. Right. We'll move on to our next topic, which is rank of a matrix. Now, this is a very, very important topic, because we'll have a lot of questions in gate papers from this particular point. Rank of a matrix. Rank of a matrix. Okay. I'll just give the formal definition of rank of a matrix first. What does rank of a matrix means? It means the number of linearly independent, the number of, you can write it down, this definition, number of linearly independent rows or columns in a matrix. The number of linearly independent rows or columns in a matrix will give you the rank of the matrix. Okay, so suppose I have a matrix A. Since I have used the word rows or columns, I can first state that rank of A is always going to be rank of A transpose. That is the first point. Rank of A will always be equal to rank of A transpose, because number of linearly independent rows or number of linearly independent columns in a matrix will give you rank, which means if I take transpose also, rank will not change, right? Rank of A is always equal to rank of A transpose. Now, the thing which we have learned in determinant is, if I have a 3 by 3 determinant, a 3 by 3 matrix whose determinant is equal to 0. Now, what does that imply? It implies there is at least one row which is linearly dependent. There is at least one row which is linearly dependent. We'll consider three different matrices with a term, a 3 by 3. I'll take three different choices. Now, my first choice is 1, 2, 3, 2, 1, 2, and 4, 2, 4. This is the first choice. This is my first matrix. I'll take another matrix B 3 by 3. That is, I'll take another matrix. Let us use different color. That is 1, 2, 3. Okay, 2, 3, 1, and 3, 5, 4. 3, 5, 4. This is the second matrix. Now we'll have another matrix. Let us consider another matrix here. The third matrix is C3 by 3 is 1, 2, 3. Okay, 2, 4, 6, 2, 4, 6, 3, 6, 9, 3, 6, 9. Okay. Now we'll explain the concept of rank using these three matrices and the idea of determinant. Okay. Now you can say that this for this particular matrix, all the rows are linearly independent. I'll tell you all the rows of this particular matrix are linearly independent. You can easily check the determinant of this particular matrix. It will turn out to be non-zero. Okay, it will turn out to be non-zero. It is not equal to 0 because 1 into 4 minus 4, that is 0, minus 2 into 8 minus 8, that is 0. Sorry, this is 0. Okay, so rank is 4 to 4. That is 1, 2, 1, 1, 2, 3, 2, 1, 2, and 1 into 4 minus 4, minus 2 into 8 minus 8, 3 into 4. Sorry, it has turned out to be determinant is 0. So I'll make it 2, 2, 2. Okay, no problem. Okay, accidentally it has turned out to be so. So consider this particular matrix now: 1, 2, 3, 2, 2, 2, 4, 2, 4. Okay, 1 into 8 minus 4, that is 4, minus 2 into 8 minus 8, 0, plus 3 into 4 minus 8, that is 3 into minus 4 minus 12, so that will be turning out to be minus 8. I think the determinant is minus 8, which means all three rows in this particular matrix are linearly independent. You cannot write one particular row. Okay, you cannot write one particular row as a linear combination of the other two. In this particular case, I have changed it into 2. Okay, I have noted your point. All these three rows are now linearly independent, which means the determinant is non-zero. If the determinant is non-zero, I can surely say that all three rows are linearly independent. And the rank of this particular matrix, the first matrix rank is going to be 3. The first matrix rank is going to be 3. Now consider the second matrix. If I consider the second matrix, this becomes, what is the determinant here? The determinant here is 1 into 12 minus 5, which is 12 minus 5 is 7, right? Minus 2 into 8 minus 3, minus 2 into 5, plus 3 into 10 minus 9. 10 minus 9 is 1, so plus 3. So 7 plus 3 minus 10, that is 0. So the determinant of this particular matrix is 0. Determinant of this particular matrix is 0, which implies at least one row is linearly dependent on the other two. So can you predict what is the rank from here? You cannot say what is the rank. I can say one thing, the rank is less than 3 because the determinant is 0. I can say the rank is less than 3 because the determinant is 0. So rank is less than 3 is the only knowledge. I don't know whether rank is 2 or rank is 1. Okay. Now I take the third matrix. Here also, if you find the determinant, 1 into 36 minus 36, 0, minus 2 into 18 minus 18, 0, plus 3 into 12 minus 12, 0. All terms are zeros, which means here also determinant of C is 0, which means I can say at least one row is a linear combination of the other two. So the rank is definitely less than 3. Now, if I cross check this matrix rank is 3. This matrix rank I don't know. I know it is less than 3. This matrix rank I don't know. I know it is less than 3. That is the only information right now I have. Right now again I am checking this matrix for rows and columns dependency information. I know 1, 2, 3. If I multiply by 2, that is 2, 4, 6. Right? 1, 2, 3. If I multiply by 3, that is 3, 6, 9. So here actually there is only one row. R1 is there. The second row is 2 times R1, and the third row is 3 times R1. So there is only one linearly independent row. Other rows are actually dependent on first row itself. So what will be the rank of this particular matrix? This matrix will have a rank of 1. Why? Because it has got only one linearly independent row. Other rows are linear combinations of the first row. First row into 2 gives you second row. First row into 3 gives you third row. Correct? Now, what is the case here? In this particular case, first row and second row are linearly independent because 1, 2, 3, you cannot scale 1, 2, 3 to get 2, 3, 1. Naturally, I know 2 rows are linearly independent now. Now, if I check the third row is actually 2 plus 1, 3 plus 2, and plus 3. So 2 plus 1 is 3, 3 plus 2 is 5, 1 plus 3 is 4. So the third row is linearly dependent on the first 2 rows. So 2 linearly independent rows are there, which means the rank of this particular matrix is 2. The rank of this particular matrix is 2. So we have 3 different 3 by 3 matrices. First one rank is 3, second one rank is 2, and third one rank is 1. And for this matrix and this matrix, determinant is 0. Now you can write one point. That is a very important point. If the determinant of a n by n matrix is 0, then rank of that particular matrix is going to be less than n. Then the rank of that particular matrix is going to be less than n. If the determinant of a particular n by n matrix is 0, then the rank of a particular matrix is less than n, which implies all rows are not linearly independent. At least one row is linearly dependent. You cannot say what is the rank from determinant, but you can say one thing, that the rank is less than n. Is it clear? Is it clear to all of you? This is a very important point. Okay. Right. Clear. Now we'll check how to evaluate the rank of a matrix using echelon form, or how do we do the echelon transformation of a matrix into echelon form. I'll do it here. That is a formal way to check the rank of a matrix. We can easily check the rank if it is n or less than n using determinant. Okay. You take determinant. If it is not equal to 0, then the rank is n. If it is equal to 0, then the rank is less than n. This is the first 2 points. You can easily check whether the rank is n or less than n. But if it is less than n, how to evaluate the rank of a matrix? That is the process which I am going to tell you now. Okay. So I have taken 1, 2, 3. I have taken 2, 1, 2, then 4, 2, 4. Okay. This is the matrix I am taking. The first point is you can do row transformations without changing the rank of a matrix. This is converting into echelon form. I think Vishnu, you can do that 4 by 4 matrix problem to evaluate the determinant using this method also, but that is going to be difficult because it involves a lot of calculations. I told you the eigenvalue method is the best method to solve that problem. We'll discuss it when we take the eigenvalue class. Okay. So the first point is you take this element as the pivot element, make it as 1, and if it is not 1, then make it as 1, and then subtract row 2, subtract sometimes of row 1 from row 2 to get this value as 0. Similarly, do for this values. So first element, I'm taking pivot element as the first element. I is equal to 1, j is equal to 1 is the first pivot element. Okay, so that is 1 here. I need not convert it into 1. So if I change row 2 equal to row 2 minus 2 times row 1, what happens? Row 2 minus 2 times row 1. Row 1 is not touched here. So row 1 remains the same. That is 1, 2, 3 itself. Row 2 is changed to 2 minus 2 times 1. That is 0. Correct? That is my idea. I need to make all the elements below this first pivot element as 0. Okay. So I convert 2, 1 as row 2 minus 2 times row 1. So 2 minus 1 into 2, that is 0. Now, second element I am taking 1 minus, see, R2 is 1, 1 minus 2 times 2, that is minus 3. 1 minus 4 is minus 3. The next operation is 2 minus 2 times 3, that is 2 minus 6, that is minus 4. Right? Now I am considering the row 3. Again, row 3, I need to convert it as row 3 equal to row 3 minus 4 times row 1. Right? Row 3 minus 4 times row 1. Again, that will be 0 because 4 minus 4 into 1 is 0. 2 minus 4 into 2. 2 minus 4 into 2 is 2 minus 8, which is minus 6. Right? 4 minus 4 into 3. 4 minus 12, that is minus 8. This is the operation I have done. Now, the first pivot element operation is complete. I'll diagonally come to the second pivot element, which is minus 3. I need to convert it into 1 first. So what I do, then the next procedure is I need to put this equal to 0. I need to do the row transformation to make this row or this element minus 6 equal to 0. So I'm converting row 3 equal to, for this particular matrix, row 3 equal to row 3 minus, okay, row 3 minus, I need to convert first this one to 1. So what I need to do, R1 divided by 3 is minus 1, correct? R1 divided by 3 is minus 1 into 6, correct? Because that will be then this becomes 2 times R1, right? Row 3 minus 2 times row 1. Row 3 minus 2 times row 1 will be 0 here. So this term will be 0. And this term minus 8 minus 4 into 2, that will also be 0. Okay. Now the echelon form is complete. You cannot take any more pivot element to convert the below elements to 0. This is the procedure. Now, this row is completely 0. This row is non-zero. This row is non-zero. This is the echelon form. Now you check number of non-zero rows in this particular matrix. Number of non-zero rows in this particular matrix is 2, which will give you the rank of this particular matrix. Okay, which will give you the rank of this particular matrix, which is 2. Is it clear? This is the idea of rank of a matrix. Now, one more thing regarding rank of a matrix, I'll explain. Do I need to repeat this process again? I mean, repeat this idea of converting to echelon form again. It's clear. No need. Okay, fine. Right. So I'll move on to the clear. It's clear. Okay, fine. I'll move on to the idea of span and rank. Span of a matrix. Span of a matrix and rank of a matrix. And rank. Okay. I'll take 2 different matrices first. I will start off with 3, 0, 0, 2. Okay. We know this matrix is nothing but 3, 0 is in this particular direction, 3, 0 in this particular direction, and 2, 0, 2 is in this particular direction. I can, in the first class, we have discussed that taking a linear combination of these 2 vectors, I can reach to any particular point in the space, right? Which means the span of this matrix is a 2-dimensional space. The span of this matrix is a 2-dimensional space. Naturally, the rank of this matrix is 2. Basically, rank will give you the dimensions which can be spanned by a particular matrix. Here, the span of this matrix is 2D space, and the rank is 2. Now, we take another example of a particular matrix. Let us say 1, 2, and 2, 4. Okay. 1, 2, and 2, 4. I draw 1, 2 is this particular line, 1 unit in the x-axis and 2 unit in the y-axis. So this is 1, 2. And if I try to draw this column 2, 4, that will actually lie on this particular line itself. That is 2, 4. Okay. Now, you take any combination of these two vectors, you'll always land upon this particular line alone, which means these two columns can only span a one-dimensional line. These two columns can only span a one-dimensional line, which means the span of this particular matrix is a one-dimensional space. So is the rank. Rank is equal to 1. So that is the relation between rank and span of a matrix. Rank will give you what is the dimension a particular matrix will span. Is it clear? So we'll take an example of a 4 by 4 matrix. Suppose I take an example of a 4 by 4 matrix. Let us say 1, 3, 4, 5. Okay, 2, 1, 0, 4. Then 3, 4, 4, 9. Then the last one is 1, minus 2, minus 4, minus 1. Okay, minus 2, minus 1. You can try to find out the rank of this particular matrix. Okay, you can try to find out the rank of this particular matrix and what is the span of this particular matrix. Which dimensional space will be spanned by this particular matrix. That you can do as a homework. Okay, is it clear to you? The idea of span and rank is clear to you? The idea of rank and span is clear to you? Okay. So okay, further. Yes. Any doubts into today's session? Okay, our topics for today is over. I'll stop recording and we'll have a discussion on your doubts. Okay.